Right, this is 7.4.2 parallel plate capacitors. So let's start off by drawing in 2 dimensions a parallel plate capacitor. And we will connect this to a DC supply. So the left plate will be charged positive, the right plate will be charged negative. Now, to increase the capacitance of a capacitor, rather than leaving it filled with air in between the 2 plates, what we do is we put something called a dielectric in between, which is an insulating material. So we put a dielectric between plates. And the dielectric is our insulating material. Which increases capacitance. So last time we mentioned that the capacitance depends on some factors. It depends on the area of the capacitors. It depends on the separation of the capacitors. And it also depends on the dielectric, or the material between the capacitors, how well it's insulated. So if we draw our parallel plates again in 2 dimensions, we've got the surface area of these capacitors, which is this area here. And what to take note of is that it's not the area of each capacitor summed up, it's the area that overlaps between these capacitors. So just the area of one plate. And this here is the separation between the plates D. So the capacitance is given by this equation. Capacitance is equal to the area multiplied by the permittivity of a vacuum, multiplied by another quantity called the relative permittivity, divided by the separation between the plates. So C is capacitance measured in farads. A is area of plate measured in meters squared. Epsilon naught is the permittivity of free space or vacuum. Permittivity of free space. This is equal to 8.85 times 10 to the minus 10 farads per meter. Epsilon R is relative permittivity. The relative permittivity doesn't have a unit. It's basically just how many times bigger the permittivity is than the permittivity of free space. So it's a scale factor. So what we could say is that the actual permittivity of the material, we could just call it, for example, epsilon, where epsilon is equal to epsilon naught times by epsilon R. Made a slight error here. 10 to the minus 12. There we go. So, I want to look at another quantity now called the dielectric constant. So what we're going to do is we're going to imagine we have a capacitor, and this capacitor has a capacitance. We're going to call this the original capacitance. We'll label it as C0. Then we change this capacitor by placing a dielectric between the plates. So here's our altered capacitor with a dielectric between the plates. And the capacitance of this capacitor increases. So our modified capacitor has now got a larger capacitance, which has increased by some scale factor multiplied by C0. So our modified capacitor is some constant multiplied by C0. And this is called the dielectric constant. If we compare then to a capacitor that doesn't have a dielectric, so with no dielectric, we've got A epsilon naught over D, because the relative permittivity will be 1 if we just have a vacuum or if we just have air in between. So the permittivity of air and the vacuum are basically almost the same. There's a negligible difference between the two. So we compare the two equations, we can see then that the dielectric constant is basically the relative permittivity. It's the same value. And finally, we're going to talk about polarization and what that means. So electrolytic capacitors are polarized. That basically means that they're marked with positive and negative terminals. If you were to connect and attempt to charge a capacitor the wrong way around, that will cause a heating effect in the capacitor, which will cause it to blow. The reason why this happens is the dielectric we place in between the plates are, while the molecules are overall neutrally charged, the atoms, the molecules themselves are electrical dipoles. So that means that while the overall charge of each molecule might be 0, the charges are concentrated on 2 different ends. Or it can even be more complicated, and it can be concentrated on 3 different ends. So before we charge, so this is during the manufacturing process, before charging, we have got our plates, and we've got our dielectric in between. So I'm just going to draw my dielectric as a dotted line. And we're going to zoom in and make the particles or the molecules within the dielectric big. So the dielectric molecules are dipole molecules. So they could look something like this, with one end's positive, one end's negative, randomly distributed. Like so. And after charging, and in a factory when they're producing these, they will charge them originally. before packaging in the sense. So they will be charged up once. After charging, we have a positive and a negative terminal. So what happens when you charge it is these molecules begin to rotate. And they will rotate due to the electric field between the plates. And so the molecules will end up looking something like this, where the negative ends of the dipole molecules face the positive terminal, and the positive ends of these dipole molecules face the negative terminal. And this is where the heating effect comes in if we plug it in backwards. Now that it's been charged up for the first time and these molecules have all rotated to be in a certain orientation, if we had to now, once this has been charged the first time, if we connect it backwards, we now have to rotate all these molecules around. And that mass rotation of molecules creates such immense heat due to the friction between those molecules that the capacitor heats up beyond what it's rated to work at. That builds up pressure within the capacitor, and if the pressure has nowhere to go, the capacitor blows up. Modern capacitors, however, they have vents on the top of them, so if the pressure builds up past a certain point, the vents break and that allows the vapor to escape. But that would render the capacitor not to its original specification anymore, so it would be useless in its application.
Do capacitors get polarized after the first charge?
Yeah, after their first charge.
So before the first charge you could do it?
So during manufacturing, before it has been charged, they're not polarized. And so what happens is they get charged, and during that same process, that's when the sleeving will be put on the capacitor to mark which side is positive, which side is negative. And they will also snip the legs of a capacitor. So the shorter leg represents a negative side. The longer leg represents a positive side. And that's the end of 7.4.2.